Hello everyone, I'm Yifan Chen from Huawei Global Training Center. Today we are going to talk about Kubernetes. To better explain Kubernetes, I want to begin with an analogy about shipping containers. Let's suppose you wanted to transport a number of goods of different shapes and size from Europe to China. There is a car, a server, several barrels of oil, and a few other items. These goods might have to be transferred several times from one carrier to another before they reach their destination, and each time they would have to be loaded and unloaded. This raises an important question. How can we ensure that the goods remain intact if we use multiple modes of transportation and have to unpack and repack them repeatedly? The answer, of course, is that we generally use containers for shipping. Once placed into containers, goods can easily be transported by sea or land without having to be unpacked and repackaged. And even though containers look largely alike on the outside, we use shipping records to keep track of what's inside. Shipping containers can even have multiple smaller containers inside them, and these can be transported by a forklift or truck after they are unloaded. This is how modern commercial shipping is made easier. We face similar problems in the IT field. For example, imagine that you have just developed a piece of software that runs properly on your development hardware, which is running a Linux operating system. However, when you install the software in another operating system for testing, it experiences a number of problems. After debugging, the software functions normally again. But then, after being deployed in a production environment, it reports error once again. We can understand that these problems may be attributable to changes in the software running environment. Different physical server models, network, operating system versions, and configurations, application server configurations, or database versions. All of these things can affect your software's performance. One simple solution would be for everyone to use the same environment. This makes sense on the surface, but there is still the human element. Different software engineers have different capabilities and preferences and may use different installation methods and configurations. These differences can also cause software problems. So the real answer is to minimize the error rate by encapsulating software into its own fixed environment, where it will not be affected by the physical servers, operating systems, network, databases, and the virtual machine environments that surround it. This is why we use software containers, and the open-source Docker platform is currently the best implementation. We have introduced the concept of containers. Now let's take a look at the differences between containerization and virtualization. As shown in this figure, virtualization means installing a piece of virtualization software or a hypervisor as a virtualization layer onto a physical server. Virtual machines running Windows or Linux operating systems reside on the virtualization layer, and applications run in them. So, with virtualization technology, each application requires an independent operating system, and running this system accounts for over 20% of the overall cost. Containerization is quite different. As we can see in the figure, each application runs in a separate container without involving the virtual machine operating system layer or the virtualization layer, hypervisor. The running environment imposes almost no extra cost, and applications perform better than those running in a virtualization environment. Virtualization systems are managed by virtualization management software, like VMware vCenter, while Docker containers can only be managed centrally with commands. However, if large number of containers are being used, or if container capacity must be expanded automatically, this can be difficult and technically demanding. As a result, a variety of container management platforms have been developed to improve the performance and management of Docker containers. There are currently 3 major open-source container management platforms: Swarm, Kubernetes, and Mesos. The Swarm project was started in 1994 in New Mexico. Swarm is now maintained by the non-profit Swarm Development Group, www.swarm.org. It allows computer programs to be distributed across multiple computers in a manner that is almost completely transparent to the programmers. The system observes the program's execution and decides how to distribute the workload to maximize efficiency. The Mesos project was initiated by the Apache Software Foundation. It tries to manage additional hardware resources beyond just managing Docker containers. Finally, Kubernetes is an open-source container cluster manager designed by Google. It works with Docker to provide a platform for resource scheduling, load balancing, disaster recovery, service registration, dynamic scaling, and automated container deployment and management. Kubernetes can schedule and run application containers on clusters of physical or virtual machines. Kubernetes has 4 main components. etcd stores the definitions and status of all of Kubernetes components. KubeAPI Server exposes the Kubernetes API and provides security mechanisms. Kubescheduler monitors pod directory changes in etcd and assigns nodes according to a scheduling algorithm, then calls the API server's behind interface to associate the nodes with the pod. Kube Controller Manager is responsible for managing master services, including nodes, pods, replication controllers, services, and namespaces. Minion Host has 2 main components, Kubelet and kubeproxy. Kubelet manages containers, images, and volumes. The kubeproxy is responsible for implementing Kubernetes and the service mechanisms with SDN features and the capability of smart load balancing in a container cluster. kubeproxy is responsible for implementing Kubernetes and the service mechanisms. It also provides SDN features and the capability of smart load balancing in a container cluster. The basic unit that Kubernetes deals with is a pod. Pods can contain 1 or more containers. For example, we have a website that uses Nginx as the front-end server, Tomcat as the back-end server, and a MySQL database in the background. All 3 of these components can run in 3 containers in a single pod. Logically, each pod can be considered a single instance of an application. Also note that pods can be moved from one minion to another. Kubernetes satisfies a number of common needs of applications running in production, such as facilitating composite applications and preserving the one application per container model, mounting storage systems, distributing secrets, checking application health, replicating application instances, horizontal auto-scaling, load balancing, performing rolling updates, resource monitoring, log access and ingestion, support for introspection and debugging, identification and authorization. Kubernetes supports Docker technology by making it possible to migrate containers across hardware resources. After you deploy a container in a pod, it can be migrated quickly from one hardware node to another, without making the user aware of any changes. Kubernetes can also work with Docker to enable rapid application scaling and migration between clouds without the need for redeployment. For example, you can migrate an software from a private cloud to AWS. Docker and Kubernetes can also work together to scale application automatically. As shown in the figure, Tomcat, Nginx, Redis, and MongoDB services can be deployed on a hardware node quickly and scaled in seconds. The auto-scaling process is as follows. First, trigger the peak clipping operation in case of traffic spikes. Second, automatically add container instances. Third, call the IaaS interface and automatically add cluster hosts. Okay, let's recap. In this section, we gave an overview of how containers work and discussed the differences between virtualization and containerization. We described 3 open-source container management platforms and then took a closer look at Kubernetes and its architecture. We also explained 3 Kubernetes usage scenarios, including container migration across hardware resources, rapid application migration across clouds, and auto-scaling. That's all for this part. Thanks for your time.